You probably think artificial intelligence exploded out of nowhere. One day we were using clunky chatbots that barely understood us, and the next, an AI was writing code, passing the bar exam, and generating photorealistic video. It feels like magic. But AI didn't just appear last year. It's been learning from us quietly for over 70 years. To understand where this is going, to understand the race toward artificial general intelligence, or AGI, you have to understand how we got here. The story of AI isn't just a story about silicon and code. It's a story about human arrogance, spectacular failures, and a multi-decade obsession with building a digital brain. Let's go back to the beginning, 1950. Meet Alan Turing, a British mathematician who, a few years earlier, had helped crack Nazi Germany's Enigma code. In 1950, he asked a deceptively simple question: can machines think? Instead of chasing a philosophical rabbit hole, Turing proposed a practical test. Imagine you're texting two different screens. Behind one is a human, behind the other is a computer. If you chat with both for a few minutes and can't reliably tell which is the machine passes. We now call this the Turing test, and it's still referenced in AI research today. Turing planted the seed. 6 years later, in 1956, a group of scientists gathered at Dartmouth College for a summer workshop. They were wildly optimistic. They figured that with enough smart people in a room for a couple of months, they could crack the core problems of machine intelligence. They didn't. But at that conference, they coined the term that would define the next 70 years: artificial intelligence. For the first few decades, researchers tried to build intelligence using what's called symbolic AI, rule-based programming. The logic seemed sound. If human intelligence is really just following rules, then to make a computer smart, you just need to write out all the rules of the world. Let's test that. Say you're teaching a 1960s computer to recognize a cat. Under symbolic AI, you write rules. Rule 1, 4 legs. Rule 2, fur. Rule 3, pointy ears and a tail. Now show it a fox. It says cat, show it a dog. Also cat, show it a 3-legged cat, and it throws an error. Not a cat because it's missing a leg the rule required. This was the fatal flaw of early AI. The real world is too messy, too full of exceptions, to be hard-coded by hand. In 1966, MIT built ELIZA, one of the first chatbots, designed to mimic a therapist. Say, "I am sad," and ELIZA would flip your sentence back, "Why are you sad?" People loved it. Some genuinely poured their hearts out to it. But ELIZA didn't understand a single word. It was pattern matching, not thinking. By the late 1970s, the illusion cracked. Governments and investors realized these rule-based systems were rigid and brittle outside of narrow lab conditions. Funding dried up almost overnight, and researchers were mocked for even working in the field. This period became known as the AI winter, a stretch where the dream of intelligent machines nearly died for good. While most of the field gave up, a small group of researchers tried something completely different. Instead of writing rules like a dictionary, they asked, how does a human baby actually learn? You don't teach a baby what a cat is by handing them a list of rules about fur and geometry. You point at a cat and say, cat. You repeat that enough times, and the baby's brain works out the pattern on its own. So what if you built a digital version of that process? That's the idea behind the artificial neural network, a system loosely modeled on how neurons connect and fire in the brain. This approach became known as machine learning. Instead of giving the computer rules, you give it data and let it discover the rules itself. The theory was solid. The problem was that to make a neural network genuinely useful, you needed two things that barely existed in the 1980s: enormous amounts of digital data and enough raw computing power to crunch through it. So for years, neural networks sat mostly dormant in academic papers. Then two things changed. The internet exploded, and humanity started uploading billions of photos, articles, and videos, solving the data problem almost by accident. At the same time, the video game industry had been mass-producing GPUs, graphics chips built to render scenes fast, which turned out to be extremely good at the kind of math neural networks need. In 2012, those two trends collided. A researcher named Alex Krzyzewski, working with Geoffrey Hinton's lab, used GPUs to train a deep neural network called AlexNet on over 1 million labeled images. It didn't just do well on image recognition, it blew past every existing benchmark by a wide margin at a competition called ImageNet. That result is widely treated as the moment the AI winter ended. Deep learning had arrived, and within a few years it was running your social media feed, unlocking your phone with your face, and steering early self-driving car projects. But AI still couldn't hold a conversation or reason the way a person does. It was extraordinarily good at recognizing patterns, not yet at generating language. Getting from there to something like ChatGPT needed one more breakthrough. In 2017, a team at Google published a research paper with an unassuming title, "Attention is All You Need." It introduced a new architecture called the transformer. Before transformers, if an AI read a sentence, it processed it roughly word by word in sequence. By the time it reached the end of a long paragraph, it had effectively forgotten how the sentence started. The transformer changed that. It let a model look at every word in a passage at once and figure out which words should pay attention to which other words, capturing context, not just sequence. The word bank next to river gets treated very differently than the word bank next to loan, and the model learns that distinction from data rather than a handwritten rule. This architecture unlocked the era of the large language model. Labs like OpenAI realized that if you scaled a transformer up dramatically and trained it on a huge slice of publicly available text, something unexpected happened. The model stopped just predicting the next word and started showing behavior that looked a lot like reasoning. Grammar, coding syntax, historical facts, argument structure, all absorbed without being explicitly taught. In late 2022, OpenAI released ChatGPT, and it reportedly reached 100 million users within about 2 months, making it one of the fastest adopted consumer products in history. For the first time since Turing posed his question in 1950, a machine was talking back to us, and it sounded unnervingly human. This was the start of generative AI models that don't just analyze data but create new data, essays, images, code, and eventually convincing video. Which brings us to right now. Where does this go next? The clearest shift happening in 2025 and into 2026 is a move from AI you talk to toward AI that acts on your behalf, what the industry calls agentic AI. Think of the difference this way. A chatbot is a consultant. You ask it to draft an email, it hands you text, and you're the one who sends it. An agent is closer to an employee. You tell it to look at a codebase, find a bug, fix it, run the tests, and open a pull request, and it goes and does the multi-step work with much less handholding. By 2026, this stopped being a demo and became daily infrastructure for a lot of software teams. Tools like Claude Code, OpenAI's Codex, and several competitors now run in extended loops, planning a task, editing files across a codebase, running tests, catching their own mistakes, and iterating for minutes or even hours before handing back a finished result, rather than a single one-shot answer. Industry estimates suggest a substantial share of code committed to platforms like GitHub in 2026 is now AI-assisted or AI-generated to some degree, though reviewers still catch a meaningfully higher rate of bugs and security issues in unreviewed AI output compared to human-written code, which is exactly why agent drafts, human reviews, has become the standard workflow rather than full autonomy. The ultimate finish line people in this field talk about is AGI, artificial general intelligence, a system that matches or exceeds average human performance across essentially any cognitive task, not just narrow ones like coding or image recognition. Are we there yet? No. Today's most advanced models still hallucinate, still struggle with long chains of rigorous logical reasoning, and arguably still lack anything resembling true understanding. They remain at their core extremely sophisticated prediction engines. But the lesson of the AI winter is worth remembering. Every time researchers assumed they'd hit a permanent wall, a new breakthrough, neural networks, GPUs, transformers, tore right through it. 70+ years ago, Alan Turing asked whether machines could think. Today, they can paint, code, and hold a conversation. Whether the next decade brings something closer to AGI or another long winter of disappointment is genuinely an open question. And it's one this generation is going to watch play out in real time.